first part of the lecture, we'll finish up acids and bases. And then the second part, we'll get into alkane functional groups, specifically nomenclature, and what the IUPAC rules are for that. We'll draw some constitutional isomers and then see why that's important. But the first part of the lecture here, again, we're going to talk about the uniqueness sets, how they match the functional groups, and then what base we would need to use to propane. Basically the weak acids. Any questions before we begin? So our first slide here, we're going to talk about, again, weak acids, so specifically CH bonds, and the effect of functional groups on acidity. So this particular slide is about resonance. And if we look at the two molecules shown here, diethyl ether and ethyl acetate, these are both common organic solvents, and the numbers in red are the pKa values associated with the different uniqueness sets. So let's just write those down for both of them. So the diethyl ether has two unique carbons, two unique sets of hydrogens. So the methyl groups are the same and the CH2 groups are the same. And we would classify both of those sets as alkanes because they're sp3 hybridized carbons. The CH bonds would have a pK of 50. And then in ethyl acetate, we have 4 unique carbons and then 3 unique sets of hydrogen in a ratio of 3 to 3 to 2. What you'll notice sort of in the left side of the molecule, CH3, CH2O, you see that as well in ethyl acetate, CH3, CH2O, and the pKa values track the same. Now, what is different in going from diethyl ether to the ester is this carbon I'm going to highlight in blue here. That's sp3, and now in ethyl acetate, it's sp2 and it's part of a carbonyl. So what I want you to focus on is that CH3 group is a pK of 50, but now in ethyl acetate it's 25. And so again, the difference between that methyl group in both of them is 10 to the 25. So that's 10 to the 25 times more acidic. And so we want to understand, why does that carbonyl group make it that much more acidic? So in our free space here, there's not much. So I'm going to draw one hydrogen coming off that sp3 hybridized carbon. And again, that carbon, since it's next to a carbonyl, we call it the alpha carbon. If we treat with some base, the base will abstract that. We break the sigma bond and put the negative charge on the alpha carbon. And so that negative charge can be delocalized up onto the oxygen through resonance. Can't tell if I'm going to go off the screen here or not. And so the stabilization of that negative charge, because they're resonance hybrids, it resides on carbon and on oxygen. And that is a reason, one of the ways to explain the increased acidity of that methyl group when you're comparing it back to diethyl ether. And so, as we said, this is an ester. And then the intermediate carbanion, this has a name called an enolate. And we'll get into those sort of nomenclatures. A lot of these words are a mash of two things. So an enolate is an alkene and an alcohol with a negative charge. So enol-ate, and ate means negative. So really what we're trying to understand is looking at a weak acid, a CH acid, how do the neighboring functional groups affect acidity? And so as we move forward, the base that we would need to use to deprotonate that pK of 25, it has to be sufficiently strong enough if we want to drive the equilibrium towards the product. So we'll spend some time talking about base strength and then associated solvents that we have to use. So again, we're moving away from water as a solvent and considering other organic solvents. So some common bases that are used are shown in this table. And let me draw a line right here. And I drew that line because if you notice in the last column, there's a big jump in the conjugate acid pKa. So the first three bases are all oxygen-based, so O minus. The first one's called sodium ethanoate. And so there's its structure. Where do I have space here? Maybe down here. So that would be that structure. Then the third column is the conjugate acid. So if you were to just protonate that, you would get ethanoic acid. And then the last column is the pKa of that conjugate acid. So even though we're talking about bases, the scale that we always use is pKa. So we always have to relate it back to that, whether it's the acid or the conjugate acid, when we're doing these comparisons. So the next is sodium hydroxide. That's derived from water. And that should be 14, sorry. And then if we take methanol, we deprotonate it, we form sodium methoxide, and that conjugate acid of methanol is 16. So a question is, how do we even form sodium methoxide? You would take methanol. Methanol is also called wood alcohol. In Prohibition days, which are long gone, people would actually drink methanol. And does anyone know what happens when you drink methanol? It's a poison, and like what eventually will happen if you consume it regularly? You'll first go blind. So later on, probably in Organic 2, we'll learn about oxidation reactions. Methanol gets oxidized to formaldehyde, which you've probably heard of. Formaldehyde then condenses with an amine in your optic nerve receptor that forms a covalent bond, which prevents an isomerization from happening. And so when that occurs, then you can no longer perceive color. So even though the federal government was trying to wean people off alcohol, which is ethanol. Humans, being what they are, circumvented the process and started drinking methanol to get the same effect, but it's a poison. So the difference in one carbon between methanol and ethanol it's huge in terms of how it's metabolized in the body. So if you take methanol, a bottle of methanol looks just like water. It maybe has a little bit of a sweet smell to it. And you take sodium metal, so just chunks of sodium. You throw it in there. You get sodium methoxide, and then you'll see some bubbling, which is hydrogen gas being evolved. And so that's how you make sodium methoxide. And basically, since the methanol is the solvent and you're adding a certain amount of sodium, the sodium methoxide is present in methanol, which is the solvent. So these alcohols they are solvents, and then they generate the base as well. So if you're looking at the pKa values based on what they are, they're relatively weak bases. So you could not use sodium methoxide to deprotonate a functional group that has a pKa of 50. It just won't happen. The next one is sodium amide, and that's the conjugate base of ammonia. So there it is, NaH2. That's actually run in ammonia as solvent as well. And the pKa of ammonia is 38. So what that's telling you is that sodium amide is a much stronger base than the alkoxides are. Ammonia, you condense it at negative 33 degrees Celsius. When it's in a flask, it looks like water, but it does not smell like water. It's very pungent. And essentially, you can do the same thing with that. You just throw sodium in there and you generate sodium amide. So now the next sort of line that I'll draw in blue here, that line is for the bases that you now generate have to use a different solvent. And because these bases are so much stronger, the solvent must be inert to that base. You can't generate the base and then have it react with the solvent, because otherwise you're not going to get your desired outcome. On the next slide, we'll talk specifically about what solvents you use, but a pretty strong base is lithium diisopropyl amide, which is abbreviated LDA. And we'll talk about nomenclature later today. What is isopropyl? It's basically 3 carbons. So that looks like Li plus. So nitrogen now has 2 lone pairs, it's minus. And then isopropyl is 3 carbons. And so there's 2 of those groups. Di means 2, isopropyl is that. So its conjugate acid is isopropylamine, and that pK is 40. So again, the larger that pKa number, that means it's a weak acid, but its conjugate base is very strong. And so at the top of the food chain here is N-butyllithium. N stands for normal. which basically means it's the one position on the chain. That's another nomenclature thing we'll talk about. So normal, secondary, tertiary, those things and how they relate to the carbon chain. So N-butyl lithium is very strong. When it acts as a base and it deprotonates something, it forms butane, which is a gas, and the pK of that is 50. So a very weak conjugate acid has a very strong conjugate base. So in the next slide, you'll see the same table, but the last column is the solvents that you would run these in. So as I said, the alcohols all just use, the normal alcohol as the solvent, and the base is generated in them. So that's this group here. Sodium amide either uses ammonia or dimethyl sulfoxide, which is abbreviated DMSO. As we move forward, a lot of things have abbreviations in there. They typically come from the name. You're just pulling out some letters. And so dimethyl sulfoxide looks like that. It's sort of like a ketone variant where the carbonyl has been replaced with sulfur. And now the last two we have tetrahydrofuran, which is a cyclic ether, and then the alkane hexane. And again, the reason that those are used, if you look at the uniqueness sets of the CHs in there, they're all alkanes. So they don't really have acidic hydrogens that can react with any of the bases. And so, for the most part, all reactions are run in a liquid solvent. So, if you take two solids and mix them together, if they were metals, they would form an alloy. But normally, two solids don't mix, so you have to have a solvent that gets everything into solution to allow the reaction to take place. The solvent, for the most part, should be inert to the reaction that you're studying. You don't want some other process happening. And the other thing, in addition to solubilizing the reactants, is solvent often serves as a heat source or a heat sink. So when we talk about thermochemistry, if you're trying to get a reaction to go forward, you can apply heat to the solvent. Or if the reaction itself generates heat, the solvent will absorb that heat. And so you can either heat them or you can cool them. If the solvent is really exothermic, you need to cool it. And so we use cryogens like ice or dry ice or liquid nitrogen to cool it at different temperatures. So there's two classes of solvents that you'll want to understand for acid-base chemistry, but also for the mechanisms that we start learning in Module 4. The first type are called protic, and they basically have an OH or an NH bond. So your alcohols or your amines, those are protic. And then aprotic solvents do not have an acidic OH or NH bond. So these tend to be alkanes, ethers, or this other one, this sulfoxide DMSO. And of those functional groups, another way to classify them is nonpolar and polar. And we know how to do that looking at the functional groups present in them, and if there's a difference in electronegativity of the bonds, whether like hexanes is nonpolar, tetrahydrofuran is polar because it has a CO bond. So here is a stoplight chart to help figure out what sort of base. So in the first column, what base you would want to use relative to all the functional groups that you've learned. And so the green light means, yes, that base can deprotonate that functional group. Yellow, probably it's dependent upon the conditions. In red, it's never going to happen. So if you're looking to do an acid-base reaction on a certain functional group, you go into column 1 to identify the base and see if that reaction will proceed. So to put that into practice, let's look at this central structure here, which is called propanone. It's a ketone. So again, it has 2 unique carbons, 1 unique set of hydrogen with a ratio of 6. And if we were to go to our pKa chart, we get that value, and we say those CH bonds are all of the ketone functional group. And so the question is sort of double-sided here. If we want to take propanone and we want to irreversibly deprotonate it, so that's what this arrow means. We want to form that carbanion exclusively. What base should we use to do that? Then to the left, notice the arrows here are back and forth, so there's this reversible equilibrium. What base should we use to do that? And so really what we're comparing is we have this value of 20. So on this side, we have some base we need to determine. Then over here we have the conjugate acid of that base. The pKa of that must be, sort of greater than 5, but really ideally much more greater than 5. And then for the other way, reversible, it can be around 20 or within that 5 or less pKa region. So let me just give you the right answer, and then we'll explain why the other ones are wrong. So the correct answer is A. So if we want to do an irreversible deprotonation, we would use LDA. So again, that's lithium diisopropyl amide. So that will deprotonate, and then it's going to form diisopropylamine. Which is the exact molecule of that BH that I've listed there. And so when you look at the pKa of diisopropylamine, that's about 38. And so 38 minus 20 is 18. That's greater than 5. So that means that that's going to do an irreversible deprotonation. I got 35 minutes to go. Hopefully I can get through it. So I'll draw it in blue. If we want to do a reversible deprotonation, we'll use potassium. And that base is tert butoxide. So O minus. And then it's attached to that 4-carbon unit called tert butoxide. So when that oxygen deprotonates, we get tert butanol as the conjugate acid. And we say the pKa of acids is about 16. And so when you look at 20 versus 16, it is strong enough to deprotonate that. But since it's less than 5, you're going to get a mixture of that ketone plus that carbon anion. Again, they'll be present in some ratio. Whereas in the other case, you're exclusively forming that carbon anion. It's not going backwards. And there are reactions where you either want it to go irreversible or you want it to form that equilibrium. And again, that's just a preview of the different types of reactions you're going to learn in Organic 1. And I think 30 of you are signed up for Organic 2 in the spring, which we'll learn some more reactions then. Choices B, C, and D. C is probably maybe the most obvious because both of these bases are the same type. They're both going to form water as the conjugate acid, and that has a pKa of 14. So if you use lithium hydroxide to do an irreversible one, it's not going to do that. It's going to do the reaction that's on the right and do the reversible. For B, the bases are mixed up. You'd want sodium hydroxide for reversible and then sodium hydride for irreversible. Again, when you're comparing the conjugate acids. And then D has the same issue as C. So let me just write. So both would be reversible. And then for D, both would be irreversible. Any questions before we move on? And then sort of switching gears, returning to a couple slides on Lewis acidic reagents. We'll see these occasionally in Organic 1, but you'll see more of it in Organic 2. A Lewis acid, as you see on the slide with BF3 and aluminum trichloride, the central metal, boron and aluminum, they're group 3 in the periodic table. So we have B, C, N, O, F, Al, Si, P, SCl. So boron and aluminum are group 3, and what you notice about them, as neutral compounds, they do not obey the octet. So they're electron deficient. And we would say they're, both of those elements are sp2 hybridized. And then they have this empty p orbital, And so that p orbital makes them Lewis acidic because a Lewis acid is an electron pair acceptor. So an electron pair can go into that p orbital. So this is an example of a Lewis acid, Lewis base reaction. On the next slide, I'll show you how they would react with an organic functional group. So it says if you have an aldehyde called butanal, so that's a 4-carbon aldehyde. The lone pair on oxygen, either of them, is the Lewis base. This is the Lewis acid. And what's implicit there is that p orbital, which I'm not going to draw, but the lone pair is attracted to that p orbital. So 2 electrons move, it will attack the boron. And so I'll add a caveat here about mechanisms, where I said before, anytime you're forming a bond, you have to break a bond. In this case, you're forming an O to B bond, but you're not breaking a B to F bond. This forms a complex. So now that oxygen is not in its neutral state, so it has 3 bonds, 1 lone pair. So its charge is going to be plus. Boron now has 4 bonds, so it's going to be negative. And the reason that these reagents exist, if I draw a resonance form, I can shift that plus charge onto carbon. So oxygen's now neutral, carbon's plus, and now that carbon atom is the Lewis acidic site. And as we learn reactions, what that means is some other species with a lone pair of electrons will attack that carbon atom. So again, as we progress through, this module moving forward, all of these fundamentals from the first 2 modules, are building on one another and helping us rationally predict where reactions happen. Any questions before we move on? So here is a drawing of that we just did using the curved arrow formalism, which is showing how that carbonyl group is now activated so that carbon atom can be attacked. So one of the things that's sort of unfortunate about, formal learning in a mass education environment is that's just like a snippet of why that's important. We're not really going to cover the subsequent stuff of that until later on. So I'm just giving you, I'm shining a light on a little bit of what that's important for. And the way your book is set up now, we're going to do a hard right and go into a completely different topic. But that's going to wrap up acid-base chemistry at this point. So any questions before we get into the last 25 minutes here? So we've yoinked the steering wheel. We're now doing a hard right or hard left, if you prefer. And we're going to introduce, now as we move forward, reactions of different functional groups. So we're starting with alkanes, which we learned about originally, and then the ring variant cycloalkanes. So here is a summary of alkanes, that general molecular formula we know. Alkenes and alkynes. So notice as you progress, you lose that equivalent of hydrogen, and then the degrees of unsaturation increases. So those are the three hydrocarbon functional groups. They're only C and H. You have C sigma bonds or C pi bonds, depending on the functional group. And overall, the reason we're starting with alkanes is because they are harvested from petroleum. So like crude oil is a mixture of various hydrocarbons, alkanes, alkenes, alkynes. And so, like BP, which is British Petroleum, Shell, all these big petroleum companies, they have sites down in the Gulf, right? They get crude oil in. Basically what they do is they crack it. They put it in a big pot, they heat it, and they're just distilling out different fractions. Probably the most common fraction that you know of is gasoline. So from, crude oil, which is like black, almost sludge, you apply heat, you distill it, you get out gasoline, which is like almost a clear liquid. If it has color to it, that's from like impurities or other additives they add. So they put a little bit of sulfur in. That's the stink of gasoline if you get it on your hand. And nowadays, because the corn farm industry is so big, ethanol that's derived from corn is subsidized by the government, and it's put into gasoline to help the farmers out. We'll talk about combustion of alkanes and why it's useful as a fuel. So when you add oxygen and a spark, it combusts. That generates a gas that pushes the piston, which turns your drive chain in your car to make it go. So ethanol isn't very good at that, but it's added, as to subsidize a different industry. So petroleum is basically the lifeblood of global economy. Pretty much everything that we use is derived from petroleum through organic chemistry. And how many people have seen that movie, There Will Be Blood? Daniel Day-Lewis, probably the best actor living. No one's seen that? Oh my gosh. Seriously, you did it just come out?
No, when did it come out?
Probably 10 years ago or so. You guys were born when it came out, so it's not like a 1980s movie.
I would have been 10. That's almost young to watch that.
So it's based on a Upton Sinclair novel called Oil, and so the character Daniel Day-Lewis plays is, I think it's in the late 1800s. He's looking for oil, and he's sort of a self-made man. He finds oil, starts selling it. He finds more land with more oil, and he eventually becomes this like tycoon, like Carnegie or whoever. But I think what's nice about this story is his character is 100% American. I mean, nothing will stop him. Not business enemies, not even his own family. I mean, it's a very good movie. If you've heard that line, "I drink your milkshake," that's from this movie. But I encourage you to watch it. It's pretty good. So we get these hydrocarbons from oil, and you've sort of seen this already. How do we name the first 10? So there's the carbon count. Alkanes have that ANE ending. Alkenes, ENE, and alkynes, YNE. Once you get past 4, the longest carbon chain prefix corresponds to like a word you're familiar with. So like pent is 5, hex is 6, so on and so forth. But the first 4, methane, ethane, propane, butane, we sort of know what those are at this point. If you're removing hydrogen to go to the alkene, then you just change that A to an E, or the alkyne, it's a Y. And so the basis for nomenclature is that you find the longest carbon chain, and that's what's called the parent. And the parent is based off one of these names. These are the rules. You can read them, I can read them. I'm not much for rules. Like any other red-blooded American, I don't like rules. But the best way to learn nomenclature is just by practicing it and doing it. And then you'll see sort of how the rules were evolved. It's not terribly complicated. You find the longest chain, you sort of circle it or highlight it, and then you number it, and then anything hanging off that chain is a substituent, which you still use that table from the prior slide. The difference now in naming substituents is if you look at this ANE ending, as my grade school teacher would say, you fire the ANE and you hire the YL. So you take the prefix of the name, you drop the ANE, and you put a YL, and that makes a substituent. So methane becomes methyl. Ethane becomes ethyl, so on and so forth. As we go through the next couple slides, what we're going to do is take C4, C5, and C6 molecular formulas. We're going to draw linear and branched isomers, and then look at how we apply those names or those rules to make those names. One very important thing through this process, what we're setting you up to learn is, yeah, you have this nonpolar alkane. The first reaction type that you're going to learn is substituting some hydrogen on that molecule for a halogen. So you've gone from nonpolar to a polar molecule. And to be able to do that, you have to be able to classify all the types of carbons and all the types of hydrogens. Even though they're all CH bonds, they react very differently. So the first column here is the type, primary, secondary, tertiary, or quaternary. It tells you how to classify the carbon or the hydrogen. And then the last are a couple of specific cases. As we've seen, a CH3 group is called methyl. CH2 is methylene. CH is methine, and carbons with no hydrogens are called quaternary. So linear hydrocarbons will only have methyl and methylene groups. Once you start branching them, then you can get the methine and quaternary groups. So there's a lot of layers to these problems that help us guide and rationally predict where a reaction will happen. So we're going to start on this slide. The structures are on the next slide, but I'm going to walk you through the exercise and the thought process here. So for the formula C4H10, that's fully saturated. We'll draw the linear and branched isomers, then we'll name them, we'll point out the classes of C's and H's so that you get a feel of this exercise. C4H10, if it's linear, all the carbons are just bonded in a line. And so that's butane. We would say the methyl groups are primary, the methylene groups are secondary. So that counts for both C and H. They overlap in that regard. For the branched C4 isomer, the longest chain has to be 3 carbons. So we would say this is going to be a propane derivative. That's the longest chain. Then we have 1 carbon to deal with. And so we need to put that 1 carbon somewhere on there. And when you're doing these branched exercises, you never put it at the end, because then you're just going to make the linear compound. So we stick 1 carbon on position 2. Since it's 1 carbon, methane becomes methyl, and we identify its position as position 2. So it's 2-methyl, and then propane, all one word. So 2-methyl propane. So numbers are separated from letters with a hyphen. Numbers are separated from numbers with a comma. That's, again, part of the rules. So for C5H12, the linear one would be pentane. So we have primary, secondary, 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 primary. If we go down to branched, the longest chain is now 4, so it's a butane derivative. We have 1 carbon to account for, so it'll be a methyl substituent, and it has to be on carbon 2. So again, that's all one word, even though it might not look like it. 2-methyl butane. So in the structure that I drew below there, the way the nomenclature rules work, 3-methylbutane is not a valid name because the substituent has to get the lowest possible number on the chain that it can. So even though technically they're the same, you cannot use 3-methylbutane. It's not correct. So we have a new class here. We have primary, primary. Carbon number 2 is now tertiary, secondary, primary. We can draw one more C5 isomer. Now we're going to take away 2 carbons, so the longest chain has to be propane. We have 2 carbons to put in there. They'll both be methyl groups, and they'll both go on position 2. So here's another layer to the nomenclature. You have to identify both of them separately. And so the way we do that would be 2, 2, hyphen. Now, since there's 2 of them, we use di. 2, 2 dimethylpropane. So for the C6, the longest would be hexane. So the next slide has all of the branched ones. So maybe what I'll do is I'm just going to draw one out, and I'll show you sort of the technique that you use to convert the structure into the name. So if you're given this structure right here, how would you then go through this process to determine the name? So the first thing you would do is identify the longest chain. And so you can do that a couple different ways, but I'll highlight the longest chain in blue. So there's really no other way you can do that. So that gets you 4 carbons. So this is going to be a butane derivative. If we number the chain, we see that anything that's not highlighted is called a substituent. So carbons 2 and 3 both have a 1 carbon substituent. So 1 carbon methane becomes methyl. We identify the positions, 2, 3 dimethyl. 2,3-dimethylbutane. So here is a chart or a table with those 4, 5, and 6 with the names generated using the nomenclature. The numbers in blue, those are the numbering of the longest chain there. And then for the 4 and 5, you see the uniqueness set. The 6, you can do that as practice on your own. Any questions before we move on? So if you want to practice this, this is called the enumeration of alkanes. It basically, in the first column, gives you the molecular formula. The second column, again, there's only ever one linear isomer. And then as you go through, you get into the branched isomers where you're successively removing one carbon unit and then placing it back on that longest chain. The last column here is showing you the total number of isomers for that molecular formula. So if you add all those numbers across a row, that's what you would get. So for C10H22, you can draw 75 different constitutional isomers. So one of them is linear, and then 74 of them are spread amongst the different branched ones. And I promise you, I've gone through 4 through 9, and I've drawn those out. I tapped out at C10 and didn't even bother. That's why there's a question mark. But again, that's good practice if you want, to learn the nomenclature, the classification, the uniqueness set. That's how you see those numbers. 1 plus 1, that gets you your 2 moving across that row. So let's see what we have up here. Yeah, maybe we'll end on this one. This looks like I was taking the elevator down the tech building from the 4th floor to the 1st floor, and this student had his phone out. It looked like he was shot. I mean, the glass on the screen was all cracked to shit. And that's kind of what that molecule looks like, a crack in the screen there. So how would we name this? So you find the longest chain, and since it's multiple choice, you're sort of given funneled into the right answer, because you need to identify the longest chain. And then once you do that, you either highlight it or circle it, and then anything hanging off of that is a substituent. So just to wrap up here, I think if we start here at the top left, 1, 2, 3, 4, 5, 6, 7, 8, 9, the longest chain is going to be 9. So that will eliminate C and D. And then between A and B, you sort of have to do this 2 ways. You number the chain one way, then you number it the other way, and you see where the substituents lie, and they have to get the lowest numbers they can. So I know we're a smidge over here, so I'm going to scooch to the next slide. So that the correct answer is A, where all of these substituents, ethyl, dimethyl, propyl, they get the smallest number they can. That's one of the rules. The location of those substituents has to get the smallest number it can, and you determine that by numbering the chain both ways. And then once you do that, you say, okay, this one abides by that rule. So we'll wrap up. You have a quiz that is due Monday at 11. So since we don't have class Thursday, Friday, I had to make it due Monday to not violate any rules. But don't forget to do that. We'll continue on with nomenclature at that point.